Hi, I am Dr. Abhishek Joshi, and in this video lecture I am going to discuss about the effect of temperatures on avalanche gain and the photodetector receiver source of noise. So let's discuss. In the previous lecture we have discussed about the different types of photodetectors like PIN photodetector, avalanche photodetector abbreviated as APD. So these two basic photodetectors we have discussed. Now we'll discuss about the effect of temperature on the avalanche gain and the source of noise. So this is the content of this lecture. So first we are going to start with the effect of temperature on the avalanche gain, then the comparison of the photodetector. So different photodetectors like PIN and APD are compared in this. Next is the photodetector receiver source of noise and the SNR calculation. SNR stands for the signal to noise ratio calculation in case of a receiver. So receiver is either PIN or APD, avalanche photodiode. So let's start with the first topic, that is the effect of temperature on avalanche gain. So a small change in temperature can cause large variations in gain. So if the operating temperature decreases and applied voltage is constant, ionization rate increases. So there will be ionization will be increasing. So there will be an avalanche gain. So this is the working principle of avalanche. So to maintain the constant gain, because we require a constant gain in any receiver, so to maintain it, electric field in the amplifying region of PN junction diode must be also changed. So this requires a compensation circuit. So we require a compensation circuit which adjusts applied voltage on the photodetector when the temperature changes. So if there is a change in temperature, so let's take the first one, that is the avalanche gain, where we have the 4 layers N plus N I P. So if you have the 4-layer structure of avalanche diode, then we can see that the photons striking on the junction, that junction which is formed increases the ionization, and the ionization depends on the temperature. So as the temperature changes, so if there is a change in temperature, either increase in temperature or decrease in temperature, the ionization changes as the breakdown of the covalent bonds. So the temperature dependent expression is given by, that is M. So M is the multiplication factor, that is equals to 1 upon 1 minus V by Vb raised to power n. So this is the voltage applied, or you can say the bias voltage, and V is the voltage. So the breakdown voltage is also dependent on the temperature. So as you can see in this figure, we are having the voltage on the x-axis and current gain on the y-axis. So as we can see, when we are comparing the avalanche photodiode with N plus, that is a 4 stack, that is N plus P, and intrinsic and P plus. So if this is 4 layers avalanche photodiode, so we can see that as the temperature changes, the junction, so this is the part of the junction, the details we have already discussed in the previous lecture. So this junction ionization is changing. So when the temperature that is T equals to 0 degrees, we can see that in the initial voltage, when the applied voltage is between 0 to 100 volt, the value is constant. Up to 50 it is constant, 50 volt. After that, the current gain, or you can say the avalanche gain, is changing. So for each case it is changing. Next one, when the temperature rises to 23 degrees centigrade, then we can see that there is a slight decrease in the gain, that is the current gain, and we follow this curve. Again, when the temperature rises to 43 degrees centigrade, Then up to 0 to 50 volt, the curve is constant, having the same, and then here we can see the gain is decreased. So this means that, and this phenomena is following, this means that as the temperature is increasing, the current gain is slightly decreasing. Now if you talk about the voltage, that is a bias voltage, and that is a function of temperature, we can write that is bias voltage as a function of temperature is equals to the bias voltage at the initial temperature. So T naught is a initial temperature, alpha is the gain, or you can say A is a constant, multiply with or function of T minus T naught, that is a change in the temperature. So T minus T naught is nothing but change in temperature, where the refractive index, so when we are talking about the change in temperature, the refractive index profile, where due to the arrangement of the atoms, the refractive index of a material is defined, which defines the how much light will be dispersed or collected. So refractive index as a function of temperature is given by NT, that is equals to the refractive index at the initial temperature, refractive index and the change in the temperature. Change in the temperature is given by T minus of T naught. So change in temperature is T minus T naught and B is some constant value. So this shows the example of how the gain mechanism of a silicon avalanche photodiode depends on temperature, and the measurement for this device is carried out at 825 nanometers, that is the first optical band. So let's compare the different diodes for different materials. So we can say the photodetectors. So when we are talking about the three basic photodetectors, that is made up of silicon, germanium and indium gallium arsenide PIN photodiodes. So this section comprises of some generic operating characteristics of silicon, germanium and indium gallium arsenide photodiodes. So when we look at the table, the list of the performance parameter for PIN and Avalanche photodiode is shown in this table, and the values were derived from various vendor data sheets and from the performance numbers reported in the literature. So they are given as guidelines for the comparison purpose. The detailed values on the specific devices for a particular applications can be obtained from the photodetector and receiver module suppliers. So we can compare the PIN photodiode for three different materials, that is silicon, germanium and indium gallium arsenide, as shown in the table in the three columns. The basic parameters are the wavelength range, the responsivity, the dark current, the rise time, the modulation bandwidth and the bias voltage. So let's compare the wavelength. So when we are using a silicon as a material, so the operating wavelength will ranging from 400 to 1100. For germanium, the range is from 800 to 1650. When we are using indium gallium arsenide, we can use a higher wavelength, that is ranging from 1100 to 1700 nanometers. So when we are talking about the responsivity, that how much the photodetector gives a response in amperes per watt. So when we talk about the silicon, it is from 0.4 to 0.6. When we are talking about germanium, it is from 0.4 to 0.5, and when we are talking about indium gallium arsenide, it is 0.7 to 0.75 to 0.95. So the dark current that is given by ID, the unit is in nanoamperes, and for silicon it is from 1 to 10 nanoamperes. For germanium it is 50 to 500 nanoamperes. For indium gallium arsenide it is ranging from 0.5 to 2 nanoamperes. So rise time is given by tau r, and the unit is in nanoseconds, and for silica it is from 0.5 to 1, for germanium it is 0.1 to 0.5, and for indium gallium arsenide it is from 0.05 to 0.5. When we are talking about the modulation bandwidth, that is B, that is in gigahertz, for silicon it is ranging from 0.3 gigahertz to 0.7 gigahertz, and for germanium it is from 0.5 to 3 gigahertz, and for indium gallium arsenide it is from 1 to 2 gigahertz. The bias voltage which is applied at the junction to work as a photodiode, we can provide the bias voltage. For silicon it is 5 volts, for germanium we can use 5 to 10 volts, and for indium gallium arsenide we have to use 5 volts respectively. So when we compare the Avalanche photodiode, again for the same materials which we have used for the PIN photodiodes, that is silicon, germanium and indium gallium arsenide Avalanche photodiodes, it's a the basic difference between the PIN and Avalanche we have already discussed in the previous lecture. Let's have a quick view on that. So for PIN photodiodes, as the name indicates, we have 3 layers, that is P, that is P type layer, I intrinsic layer, and N, that is N type layer, that is in the reverse bias. So that is a PIN photodiode, abbreviated as PIN photodiode. When we talk about the Avalanche photodiode, it is N plus, P, I and P plus. So these are the Avalanche photodiode. This is a 4-layer device. So this is the Avalanche photodiode. So let's compare the Avalanche photodiode for the 3 different materials, that is silicon, germanium and indium gallium arsenide. So the wavelength for the Avalanche photodiode, when we compare this for the material silicon, then we have 400 to 1100 nanometers of wavelength. When we talk about germanium, it is 800 to 1650 nanometers. For indium gallium arsenide, again we are getting the same performance, that the higher wavelength region ranging from 1100 to 1700. When we are talking about the Avalanche gain, that is a multiplication factor, that is capital M. So for silicon it is ranging from 20 to 400, for germanium it is 50 to 200, for indium gallium arsenide it is ranging from 10 to 40. So when we talk about the dark current, the dark current unit is in nanoamperes. So for silicon it is 0.1 to 1 nanoamperes. For germanium we are getting some higher value, that is 50 to 500 nanoamperes, and dark current we can see here in indium gallium arsenide it is from 10 to 50. When we talk about the rise time in nanoseconds, so for silicon it is ranging from 0.1 to 2, for germanium it is 0.5 to 0.8, for indium gallium arsenide is ranging from 0.1 to 0.5. When we talk about the gain bandwidth product, because in Avalanche we have the gain, so that is also known as the Avalanche gain, and when we multiply this Avalanche gain with the bandwidth of the signal, then we are having M into B, that is the gain bandwidth product. So that value will be in gigahertz, and for silicon we are having the range that is from 400 to 400, and for germanium it is from 2 to 10. For indium gallium arsenide, the gain bandwidth product is having the range that is 20 to 250. When we talk about the bias voltage, so the bias voltage which we can apply to the diodes in the reverse bias, that it is ranging from 150 to 400 volts, while germanium is operating at the lower voltage, that is 20 to 40 volt, and for indium gallium arsenide we require 20 to 30 volts. So for short distance application, silicon devices operating around, that is the first optical window 850 nanometers, provide relatively inexpensive solutions for most links. So longer links usually require operation in 1300 nanometer and 1550 nanometer windows, that is the second optical window and the third optical window. So one normally uses indium gallium arsenide based devices for higher region. As we can see, the response in the second and third optical window is good as compared to silicon and germanium. So let's discuss about the photodetector receivers and its equivalent circuit. So this is a simple model for the photodetector receiver. So we can see here we have the photodiode. So in this photodiode, it may be PIN photodiode or Avalanche photodiode, abbreviated as APD. So here we are applying the bias voltage. So bias voltage, so we have to keep this diode in the reverse bias. So bias voltage is applied here and it is applied to the N. So this means the higher voltage will be applied to keep it in reverse bias. So high voltage. So the positive, that is a P side terminal, is applied to the ground via the load resistance RL. So when we are applying through this, now when we apply the external photons or the external energy, that is abbreviated as H nu, the junction breakdown, and we can see there is a flow of the current inside this diode. It may be PIN or the Avalanche photodiode. Next, we have to amplify the small signals which we have received, electrical signal. Then this electrical signal is amplified and then we are getting the output. So the equivalent circuit for the same, we can design the equivalent circuit. So here we can see we have the photodiode and the external energy given by H nu. So it may be anyone, PIN or APD. Then we can see that there is a series resistance. So this is the series resistance and the capacitance of the, due to this dark current, we can see the capacitance CD, and the load resistance RL, load resistance is RL, and due to the amplifier we can have the amplifying resistance, and due to the capacitive effect of the amplifier we have the amplifier capacitance, and finally the amplifying version of that. So there are different noises present at the receiver. So this figure shows a block schematic of the front end of an optical receiver and the various noise sources associated with it. So the majority of the noise sources shown applied to both. Here we can see in this figure, we have the optical signal which is received. So here we can have some wavelength, or you can say the optical signal, let's say it is some lambda wavelength, and it is striking the junction of the photodiode. So photodetection process take place. So here we are having some photodiode, it may be PIN photodiode or Avalanche photodiode, and this photodetector is providing the electrical signal. Now this optical signal from here, it is converted to electrical signal. Okay. Now once we got the electrical signal, we can have the multiplication, or you can say the gain. So there will be amplifying factor, and this is given to the detector bias, load bias, and the amplifier is amplifying this signal. Now here in this photodetection process, we may have different source of noise. So different source of noise may be the quantum noise, the dark current noise, the background noise, or the beat from the incoherent carriers. So noise in the avalanche gain, when we are talking about the noise in the avalanche photodiode, so it is due to the excess, due to the random gain mechanism. It happens in avalanche photodiode due to the excess of random gain mechanism. So detector load bias, so when we talk about the detector load bias, we have the noise that is due to the change in temperature, which we have discussed in the previous slides, and due to the change in temperature, the noise, we have introduced the noise, or the detector is introduced by the noise. So when we are using a electronic gain, or you can say the electronic amplifier, to amplify this electrical signal, because this signal will be very weak, so we have to amplify it again. So there will be a source of noise. So first source of noise will be the thermal noise due to the input resistance. Now due to the active element which amplifies it, So the devices, we are having the noise due to the active elements, and due to the surface leakage current, we are having the third part of the noise. So there are three basic source of noise in electronic amplifier. So this is a block schematic of the front end of an optical receiver showing the various sources of noise. So these are the various sources of noise in a receiver or optical receiver. So let's discuss the next important parameter for the receiver, that is SNR. SNR also stands for signal to noise ratio. So the SNR can be defined, that is the signal power from the photocurrent, that is with the noise power, that is the photodetector noise power plus the amplifier noise power, that is signal to noise ratio, that is SNR. So to achieve a high signal to noise ratio, the following conditions should be met. So what are the conditions? The first condition is the photodetector must have a high quantum efficiency to generate large signal power. Second one is the photodetector and the amplifier noises should be kept as low as possible. So how we can define? So signal to noise ratio is nothing but the signal power from the photocurrent, and the noise power is from the photodetector noise power plus the amplifying noise power. So this is a combination of these two. That's why we have to keep the photocurrent, that is given by IPH, that is equals to the efficiency multiply with a charge Q divided by the external energy given by E is equals to H nu, and multiply with the power which is provided, or you can say the optical power. So for a PIN photodiode, the mean square signal current, that is I square. When you talking about the I square, we can find the power. So I square as current, that is given by the variance of the signal of the PIN photodiode, that is sigma s square, that is equals to the mean square value, that is the expectation of IP square, we can say. Or for avalanche photodetector, the same can be written, that is I square S, that is sigma s square for avalanche photodiode, that is equals to IP square T into the avalanche. So one additional factor is there in the avalanche photodiode, that is M square. So M square is the avalanche multiplication. So we have to multiply this factor also in a avalanche photodiodes. So we can find the noise power. So we can find the noise power simply by I square, the mean square value of the noise, that is I n square, that is equals to sigma n square. For the short noise, for the we are having others noise also. So that is I square dB, I square ds, and that is equals to sigma short square plus sigma square dB, sigma square ds. So when we substitute the values of the different source of noise, we can write it as the twice of Q, that is charge, IP photocurrent, dark noise current, that is ID, M square is the avalanche multiplication factor, FM, and the bandwidth BE, and the twice of charge and the leakage current IL and BE. So the total current we can find, that is I square T, that is equals to, that is 4 times KT BT by RL. RL it is a load resistance, or you can say that for the transistor, and BE is the bandwidth. So signal to noise ratio. So substituting the value of the signal as well as for the noise in this expression. So noise is divided. So this expression we have substituted here, and the source of the signal is given by, so here we can write the source of the signal, that is I square P M square. So I square P, this is for the avalanche signal power. Avalanche signal power, that is IP square M square divided by 2Q IP plus ID M square FM BE plus 2Q IL BE plus 4 times KBT BE by RL. So signal to noise ratio is given by IP square M square 2Q IP M square FM BE plus 4 KBT BE by RL, that is the load resistance. So this is the signal to noise ratio for avalanche photodiode. So in this lecture we have discussed about the effect of temperature on avalanche gain. the comparison of photodetectors, then the photodetector and the receiver sources of noise, and the SNR calculation. So we have covered this topics in this lecture. So we have referred this optical fiber communication by the John M. Senior and the optical fiber communication by Grad Kaiser to prepare this slides. Thank you.